Hello everybody. Last stream we finished with our chapter 5 structs and actually method syntax for the structs. Let's quickly look how it was. Yeah, so this is concept of implementation where we can add uh, function to the struct, like function to the type. If you, for example, using JavaScript, like for rectangle object, you can add some functions. Something like this. Also, there was some concept about associated functions. This is where we don't use self. Self is like, yeah, in previous example, let me find it. In previous example, we use an entity of the structure. Like here, we create a rect entity, and then when we use the function, we use entity of it, and it's called self. And for associated functions, we don't use self. We don't pass it as a parameter to our method, so we don't actually need the entity, so we can use it rectangle as a namespace. Let me find it. Yeah, actually something like this. Okay, now today we're going to learn about enums and pattern matching. So let's start. In this chapter, we will look at enumeration, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we'll look at how pattern matching in the match expression make it easy to run different code for different values of an enum. Finally, we will cover how the if-let construct is another convenient and concise idiom available to handle enums in your code. So option, if I'm not wrong, is something like I guess it's alternative to have try-catch construction. If I'm not mistaken, I saw people really loved it about the Rust. Much we saw it in the chapter 2. It's also a cool feature. And if-let construct, yeah, if you may be familiar with the Swift, I guess it's something similar, but yeah, just my guesses, and let's find out. So started with section 6.1, defining an enum. Defining an enum, where structs give you a way of grouping together related fields and data. Like a rectangle with its width and height, enum give you a way of saying a value is one of possible set of values. For example, we may want to say that rectangle is one of set of possible shapes that also includes a circle and triangle. To do this, Rust allows us to encode these possibilities as enum. Let's look at a situation we might want to express in code and see why enums are useful and more appropriate than struct in this case. Yeah, so basically, I don't know if you familiar with, maybe not any, like in JavaScript there is no enums, but you can create something kind of this, but in a TypeScript or whatever. It's C++, Java, I guess. I don't remember about Java, but I guess something like this exists there. So you just have enumeration like rectangle, circle, triangle. I don't know. Let me quickly show you. I don't know, any TS file. So we can do enum, have color, no. So and then you can just use it something like color, black. Basically, if you have some function which receive the color, and then you can do switch case, something like I don't know, for example like this, based on the color. But yeah, the idea is following enumeration. You have like definite amount of different cases, and you know when you see it's not just 1 to 3, but it has some meaning. It means some color. Or maybe color is not the best example. For example, I don't know, let's have switch and something like this, on, off, etc. Yeah, but actually not so important. Let's back to our book. Just maybe remind myself what is enums in different languages, and let's compare how it will look in the Rust, if there anything special about it. So let's look at situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with API addresses. Currently, two major standards are used for API addresses, version 4 and version 6. Because these are the only possibilities for an API address, then our program will come across. We can enumerate all possible variants, which is where enumeration gets its name. Okay. An API address can be either a version 4 or a version 6 address, but not both at the same time. That property of API address make the enum data structure appropriate because an enum value can only be one of its variants. Both version 4 and version 6 addresses are still fundamentally API addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of API address. We can express this concept in code by defining an API address other kind enumeration and listing the possible kind an API address can be v4 and v6. They are the variants of the enum. So API other kind is now custom data type that we can use elsewhere in our code. So as usually we see some snippet, we should try it ourselves. So let's have enum IP other kind, then v4, not v5 but v6, like this. Cargo run is working, so it's fine. So enum values. We can create instance of each of the two variants of API other kind like this. Okay. Of course, let's do this. Or okay, Copilot already get it. Yeah, some warnings, but still running, so we are fine. Note that variants of the enum are namespaced under its identifier, and we use a double colon to separate the two. This is useful because now both values v4 and v6 are of the same type. No, actually, interesting. So type is IP other kind, and the value is v4 and v6. We can then, for instance, define a function that takes any IP kind, IP other kind. Let's of course do this. Fn route IP kind. We're not going to implement body of the function. Let's just quickly run to see if there are any mistakes. No, we're good so far. And we can call this function with either variant. Yeah, that's basically clear, but let's quickly make sure everything is working. Okay, good. Using enum has even more advantages. Thinking more about our API address type. At the moment, we don't have a way to store the actual IP address data. We only know that what kind it is. Given that you just learned about the struct in chapter 5, you might be tempted to tackle this problem with structs as shown in listing 6.1. So now we can create a struct IP address and have two fields, kind of type our IP address kind address and an actual string address. Let's do this. Struct IP. I don't like address. Let's have full address word. The kind will be other kind, and address will be string. And now let's create home. Kind will be IP and address string from and semicolon here. And loop back. It's nothing special about this like construction, but just for sake while we're reading, we do some practice, we kind of get ourselves more familiar with the syntax of the Rust. So just doing like small exercises by writing these kind of examples from the book. Pilot already knew all the symbols. I guess a lot of people already tried exactly from the book. But anyway, let's as usually run to see if we do any mistakes. No, it's still running. And let's continue. Here we define a struct IP address that has two fields, a kind field that is of type IP other kind, the enum we defined previously, and an address field of type string. We have two instances of this struct. This first is home and it has the value v4 as its kind with associated address data of usual localhost address 127.0.0.1. The second instance is loopback. It has the other variant of IP address kind as its kind value, so v6, and has address double semicolon 1 associated with it. We used a struct to bundle the kind and address value together. So now the variant is associated with the value. However, representing the same concept using just an enum is more concise rather than an enum inside a struct. We have put data directly into each enum variant. This new definition of the IP under enum says that both v4 and v6 variants will have associated string value. This is actually it's no, it's actually different. Yeah, I'm thinking about the cases I used enums previously in different program languages, and this one actually is different. So we have type like enum type v4. We can associate some dynamic value with it. So this is interesting. Let's try. Maybe let's remove everything here. Remove the struct, and here what we can do, and for will like home and loop back will be current v6 string from something like this. Okay. And yeah, I'm kind of curious how we can use it. So we attach data to each variant of enum directly, so there is no need for an extra struct. Here it's also easier to see another detail of how enum work. The name of each enum variant that we define also becomes a function that constructs an instance of the enum. That is, yeah, basically, and how we did it previously, yeah, it wasn't a function, it's just like v4, and here v4 in parentheses, so it's become a function. This is IP address v4 is a function call that takes a string argument and returns the instance of the IP other type. We automatically get this constructor function defined as a result of defining the enum. There is another advantage to using a enum rather than a struct. Each variant can have different types and amount of associated data. So yeah, this is interesting. We can associate different different data with each type. It's really interesting. So version 4 API addresses will always have 4 numeric components that will have values between 0 and 255, so it's like 8, actually 8 bits, 8 bits. If we want to store v4 address is 4 u8 values, but still express v6 addresses as one string value. We wouldn't be able to with a struct, and Enum handled this case with easy. Yeah, with struct it will be harder to do this, so we maybe had to create different structs for each case. This is quite interesting. So let's do this. Okay. We've shown several different ways to define data structures to store version 4 and version 6 IP addresses. However, as it turns out, waiting to store IP addresses and encode which kind they are is so common that the standard library has definition we can use. Okay. But you see it receive the type and IPv4 address is struct okay, not important, but let's look at how the standard library. Oh, okay, here is it exposes explanation. How standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of two different structs, which are defined differently for each variant. So yeah, two struct, and each handle their own behavior. This code illustrates that you can put any kind of data inside an enum variant, string, numeric types, or structs, for example. You can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. This is actually a quite cool sentence. It has like the idea I faced myself. For example, in the React.js world, there was an Redux, and you think about Redux is some magic library, it's doing something outstanding stuff. But then I saw the course of Dan Abramov, which implemented from scratch, and it's quite simple what is happened underneath of this. So if you have a chance to see how things implemented in the first place, you will be surprised how maybe it's quite simple, but you level up yourself of understanding as a client user of these APIs on several next levels. This is a cool one, yeah. Note that even through so the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library definition into our scope. We'll talk more about bringing types into scope in chapter 7, which is next chapter. It's, yeah, I'm always happy when I see next chapter, not like chapter 20 or something, because it happens soon. So let's look at another example of the enum enlisting 6.2. This one has a wide variety of types embedded in its variants. So enum message, okay, and as usually, let's write it down by our hands, and Copilot already know what we're going to type, but still we will do it. Yeah, sometimes I'm just pick some suggestion, but generally I would like to write everything myself. I think I don't understand yet the move role. Change color. Oh, I did a mistake. No, it's fine. So it don't have associated type on queued here. On move, it looks like a struct, but without a name. Like it's, I don't know how it's properly called in Rust. Right, have string associated type and change color. Just accepts 3 I set it to number. So let's read explanation. This enum has 4 variants with different types. It has no data associated with it at all. So, okay. Move has named fields like a struct does. So this is like a struct as I expected, but not exactly. Write includes a single string. Yeah, this is obvious one. And change color include 3 I32 values. This is kind of clear as well. Defining an enum with variants such as the ones in listing 6.2 is similar to defining different kind of struct definitions, except the enum doesn't use struct keyword and all the variants are grouped together under the message type. The following structs could hold the same data that the preceding enum variants hold. So here we're representing the data in structs. This is tuple, this is tuple, and this is regular one, and this is struct with no data. But if we use the different structs, each of which has its own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6.2, which is a single type. Yeah, I almost can feel the power of it, since I guess we can do implementation functions for enums as well, but I'm kind of do have feeling some, but don't complete understanding everything yet, but have this excitement inside of me. So there is one more similarity between enums and the structs. Just we were able to define methods on the struct using implementation. We're also able to define methods to enums. Here the method named call that we could define on our message enum. Yeah, as we expected. It was mentioned, I guess, in section 5.3. So imp message or scope. Here we can do a file call reference to self and just test run. Everything is fine here. Yeah, maybe message right, then put string here from hello, and then we can do the call. Still doing nothing but check if it's compiles. Okay. The body of the method would use self to get the value that we called the method on. In this example, we created a variable m that has the value message write string from hello, and that is what self will be in the body of the call method when m call runs. Let's look at another enum in the standard library that is very common and useful option. Yeah, this is something really interesting should be here. So the option enum and its advantage over null type, null values. This section explores a case study of option, which is another enum defined by the standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing. So I guess we can, for example, fetch data from the network. In case of success, there will be some data and it will be something, and in case of error, the data will be nothing. So Yeah. For example, if you request the first item in non-empty list, you will get a value. If you request the first item in an empty list, you would get nothing. And good example, actually today I fixed the bug related to the TypeScript. When you take item from the array by an index in the TypeScript, it says to you that you will have the type of item of array, but in case the array is empty array, it will actually undefined, but TypeScript not catch this problem. So yeah, and this undefined cause a crash on the website I was working on today. I think this problem will not be happen here in the Rust world, so this is why everyone's so excited about it and looking. And yeah, this is Stack Overflow programming language survey year by year. It's most loved language. So yeah, sorry for the lyrics. Let's continue with the book. So for example, if you expressing this concept in terms of type system means the compiler can check whether you handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Yeah, one of it we just discussed. Programming language design is often thought of in terms of which feature I include, but the features you exclude are important too. Rust doesn't have the null feature that many other languages have. Null is a value that means that there is no value there. In languages with null, variables can always be in one of two states, null or not null. Yeah, before I don't even like think about there is could be the way where we don't have null, because like there is natural binary state, it's exist or not exist, 0 or 1. This is quite interesting concept. In his 2009 presentation, Null References, the $1 billion mistake, Tony Ho, let me, Ho, okay, robot says it's pronounced like Ho, Tony Ho, oh, the inventor of Null has this to say. Oh, Null has its own inventor. I call it my $1 billion mistake at that time. I guess we can easily say $1 trillion. At that time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. Wow, this is exciting story. impressed me. Let's continue. What our option and I'm doing here. The problem with null values is that if you try to use a null value as a not null value, you'll get an error of some kind, because this null or not null property is sorry, I need pervasive, because this is null or not null property is pervasive. It's extremely easy to make a kind of error. However, the concept that null is trying to express is still a useful one. Null is a value that is currently invalid or absent for some reason. The problem isn't really with the concept but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that call encode the concept of a value being present or absent. This enum is option t. This is called generic usually, I guess same in the Rust, and is defined by the standard library as follow. As usually we have a reference and we click all the reference, just swiftly look what's going on. In the documentation there is so there is implementations and different functions we can use in for this enum option. Oh, there is actually a lot of them. Like we can iterate. So yeah, really interesting. But basically none is option with no associated data, and some is field with associated with some data of type which we're supposed to define. The option t enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. So prelude is something automatically available in our scope from the standard library. But before, like, for example, IP address is not, it's in standard library, but it's not available by default. In our scope, we should explicitly bring it, which we will know more about it, I guess, in chapter 7. So yeah, so we can use it without any additional actions. You don't need to bring it into the scope explicitly. Exactly, its variant are also included in the prelude. You can use some and none directly without an option prefix. Without it, okay. The option t enum is still just a regular enum, and some t and none are still variants of type option t. Okay, the angular brackets, is it called angular brackets? Angular brackets. Yeah. The angular brackets T syntax is feature of Rust we haven't talked about yet. It's generic type parameter. Exactly. And we'll cover generic in more detail in chapter 10. For now, you'll need to know is that T means that the sum variant of the option enum can hold one piece of data of any type, and that each concrete type that gets used in place of T makes the overall option T type a different type. Here are some examples of using option values, a hold number types and string types. Okay, to hold number type and string types. Okay, this is sum, and this is none. I don't really type it, but let's have it in our example code. So core option sum T, sum of type T, and you see what generics do. It replaces T with actual type. In this case we used the number, which automatically cast it to I32, and here we have option char. So this one was a char, and what we have here, yeah, here we explicitly defined it I32, but it's actually, yeah, it's type option, but the value is none. Okay. Okay, good. The type of some number is option I32. The type of some char is option char, which is a different type. Rust can infer these types because we have specified value inside the sum variant. For absent number, Rust requires us to annotate the overall option type. The compiler can't infer the type that the corresponding sum variant will hold by looking only at a none value. As we tell Rust that we mean for absent number to be of type option angle brackets I32. When we have a sum value, we know that the value is present and the value is held within the sum. When we have a none value, in some sense, it means the same thing as null. We don't have a valid value, so why is having option T any better than having null? This is quite a good question. In short, because option T and T where T can be any type are different types, the compiler won't let us use the option T value as if it were definitely a valid value. For example, this code won't compile because it's trying to add an I8 to an option I8. So x is 5 and y is option and sum is 5. So we cannot do the sum operation because it's not explicitly 5, it's option of I8. So if we run this code, we get an error message like 1. Cannot add option. Yeah, this is obvious kind of for me. And help the trait and is not implemented. The following. Yeah, it's not really important for us, I think. Intense. In effect, this error message means that Rust doesn't understand how to add an 8 I8 and an option I8 because they're different types. When we have a value of a type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for a null before using that value. Only when we have an option A8 or whatever type of value we're working with do we have to worry about possible not having a value, and the compiler will make sure we handle that case before using the value. In other words, you have to convert an option T to a T before you can perform T operations with it. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is. Yeah, this is actually what we expect from, for example, TypeScript when we migrated from JavaScript. It will say us there's possibly something undefined and you should do maybe additional, wrap it with additional if or something, but it not always can know, like in the runtime, if it's the variable there or not. In this case, the Rust solved this problem. I guess we haven't tried yet, but I guess what it says, you always forced to do the check, and only in case there is a value we will work with this value. Yeah, this is like, sounds like something bulletproof solution. So eliminating the risk of incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of the value option T. Then, when you use that value, you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an option T, you can safely assume that the value isn't null. There was a deliberate design decision for us to limit nulls pervasiveness and increase the safety of Rust code. So how do you get the T value out of some variable when you have a value of type option T? So that you can use the value. Value option T in Enum has a large number of methods. We actually saw it here. Quite large number of methods. Large number of methods that are useful in a variety of situations. You can check them out in its documentation. Become familiar with the methods, and option T will be extremely useful in your journey with Rust. Yeah, maybe we will like have some stream where we check in all possible option function, but I think we still not there yet. You're not needed right now. In general, in order to use option T value, you want to have code that will handle each variant. You want some code that will run only when you have some T value, and this code is allowed to use the inner T. You want some other code to run only if you have a none value, and that code doesn't have T value available. The match expression is a control flow construct that does just this when used with enums. It will run different code depending on which variant of the enum it has, and that code can use the data inside the matching value. So in this section we find that there is an option, but actually to use it we need to dive into another section, which we are not going to do today, but we will continue next time. Thank you for watching. See you next time.